This is lesson 4.5 on exponential equations. So in the last lesson, we looked at the graphs of exponential functions. Now we didn't mention this explicitly, but it's a very important fact that our exponential functions are one-to-one functions. So this shouldn't be a surprise, because if we think about what the graphs of our exponential functions look like, they very clearly pass our horizontal line test. So exponential functions, since they're one-to-one, remember the definition of that means that if we have two exponential functions with the same base equal to each other, the only way that can occur is if the exponents are the same. So in this example here, 2 to the a equals 2 to the b. If that's true, that means a equals b. The only way that two numbers, two exponential terms, functions with the same base can equal each other is if what's in the exponent is also equal. So this is the key fact that we use when solving exponential equations. So an exponential equation, as the name implies, it's going to be equations involving exponential functions. The ones that we are going to see for our drill problems, we're going to be able to write them as a single exponential function on either side. So on the left-hand side, we will be able to write the phrase as a single exponential function. On the right-hand side, we'll be able to write it as a single exponential function. So left and right-hand sides we can write as just a single exponential function. What's even better is if we can get it into the case that we just saw, if we can get things in terms of the exact same base on the left and the right-hand side. For our drill problems, we are going to be able to do just that. So we're going to take the left-hand phrase, the right-hand phrase, rewrite both sides so that they are in terms of the same base. Once that occurs, drop the bases, set the exponents equal to each other, and solve for x or y or whatever variable we'll run into. We'll likely see x, but don't go crying if a y pops up. So get it in terms of the same base, drop the bases, solve for x. That's all there's going to be to it for these problems. So here's an example. Solve 4 to the 3x minus 1 equals 32 to the x plus 1. Now most of the time, 9 times out of 10, 99 times out of 100, the problems that we are going to see are going to involve powers of 2, 3, or 5. So here, 4 and 32, we want to write those as some power of the same base. So here I think both of these we could write as a power of 2. So 4 I know is just 2 squared. So I'm going to write this as 2 squared to the 3x minus 1 power. So I've replaced the 4 with 2 squared. I'll do a similar thing with 32. 32 I'm pretty sure is a power of 2, but maybe I'm not certain. Let me just make some scratch work here. 2 times 2 is 4. Times 2 is 8, times 2 is 16, times 2 is 32. Okay, so this is 2 to the 1, 2, 3, 4, 5th power. So 2 to the 5th power to the x plus 1 power. So see what I did here? 2 became 2 squared, 32 became 2 to the 5th. Remember the way that we handle when we have some number raised to an exponent, that is then the whole thing is raised to the exponent, raised to some power. So notice that 2 squared is what's being raised to the 3x minus 1 here, not just this single 2 here. So that means we're going to multiply these two numbers. So this is 2 to the 6x minus 2. I multiplied 3x minus 1 times 2. Over here, similar story. I'm going to say 5 times x plus 1, so 5x plus 5. So notice now I have exactly what I want. 2 to some power equals 2 to some other power. I'm going to drop the bases. So the only way these two things can be equal is if their exponents are equal. So I'm going to solve for x, subtract 5 from both sides, add 2, I get x equals 7. So here's another one. 27 to the 4 minus x equals 1/9 to the 2x plus 1. Now don't let your fractionophobia just freeze you up here. Remember, whenever we see a fraction for these problems, it's almost certainly going to be basically, again, 2, 3, or 5 to some negative power. So just because we see a fraction here, don't worry that, oh, we've got to do everything in terms of fractions now, and that's just going to ruin my afternoon. Don't worry. Think about how can I rewrite this as some negative power of a number that I know. So 27, I see, so 27 here, 9 here. I'm probably working with 3's this time. So 27, let's see here, 3 times 3 is 9, times 3 is 27, so this is going to be 3 cubed to the 4 minus x. Then on the right-hand side, I know that 3 squared is 9, so 1/9 is going to be 3 to the negative 2, to the 2x plus 1. All right, so same deal as before. I multiply the exponents, so 3 to the 12 minus 3x equals 3 to the negative 4x minus 2. Same base on both sides, just a single term, so I can drop the exponents. And then just like before, I solve. So let's see here. So I'm going to add 4 to both sides, so that gives me x. Subtract 12 from both sides, gives me negative 14. So these are fairly quick and simple problems. You just have to remember, rewrite each side as some power of the same number. Almost certainly it's going to be a power of 2, 3, or 5. This works for any number. If we run into equations with e in it, that's fine. If we run into equations with powers of 2/3 or 15 or whatever, it doesn't matter that it's those three numbers, 2, 3, and 5. I've picked those three numbers simply because it makes life easier for us. Beyond the scope of our drill problems, it's quite likely that we will see problems that aren't using bases just 2, 3, and 5. But it's okay. The same technique works when we can get it to work. Now, if we cannot write it as a single term on the left-hand and the right-hand side of the equation of the same base, we're not completely out of luck, but we just unfortunately don't have the tools to handle those right now. So for this particular section, any equation that we run into, we will be able to write it as some power of some number using the same base. So be aware of that. On our application problem, again, we'll be able to write things in terms of the same base, but it'll be perhaps just slightly different, just a little bit more work than what we have here with our drill problems. So here's a scary looking one. So right off the bat, I hope that we recognize that this is significantly different from what we've seen before. The main thing that I want to point out here is notice that here on the left-hand side of the equation, we've got two different terms. We really don't like that. We do not like handling two different terms. For our exponential equations, we really want to have some exponential function equals some other exponential function. Preferably, even in that, we like for those to be two exponential functions with the same base. But later we will learn a technique of how we can solve those even when they don't have the same base. It's a little bit more work, but we can handle it. Here what we need to do is we really want to be able to write this as just a single term. So the technique that we're going to learn here is focus on writing each side as just a single exponential function. You say that just one more time. Another technique that can pop up here is these equations are frequently in the form of what we learned in a few sections ago of the quadratic type. Here we know that that's not going to be the case. We've got two giveaways. The first giveaway is we've got an exponential term over here that's to some variable power. If we've got exponential functions on both sides of the equation, we're probably not going to be dealing with something that's of quadratic type. The other giveaway is notice that the power of these two things, one is not twice the power of the other. So this is not a good candidate for quadratic type. There are problems that pop up where that's the key, but this is not one of them. Here what we want to do is I'd recommend factor out the exponential function, the largest exponential function term that you can. So 4 times 3 to the x minus 3 to the x plus 1. So we've got two exponential terms with the same base. Factor out the term with the smaller power. So here we're going to factor out a 3 to the x. So if I factor out a 3 to the x, what I have left from this term is just going to be 4. And this 3 to the x plus 1, it's going to be 3 to the x plus 1 minus x, because I factor out a 3 to the x term. So that's going to leave just a 3 to the first power term. So 4 times 3 to the x, when I factor out a 3 to the x, I'm left with 4. 3 to the x plus 1, when I factor out a 3 to the x, I'm left with just 3. So we notice that that's going to simplify pretty nicely, aren't we? On the right-hand side, do what we've been doing before. Write this as some power of 3. So 1/3 I know is 3 to the minus 1 power. So I'll just leave it like that. So on the left-hand side, 4 minus 3, we know that's just 1. So on the left-hand side, we have 3 to the x. On the right-hand side, we've got 3 to the negative 1 to the 2x minus x squared. So that's going to be 3 to the negative 2x plus x squared. So we've got exponential function base 3 equals exponential function base 3. Drop the bases, set the exponents equal to each other. Okay, so if I move everything over to the right-hand side, I have 0 equals x squared minus 3x. If I factor out an x, I have x times x minus 3 equals 0. So the only way that that can work is if x itself is 0 or if x equals 3. So my two solutions are going to be x equals 0 and x equals 3. So we have two things that are a little bit different here that we did not see in our drill problems. The major difference, here we have multiple terms. We really don't like that. So at all costs, see if you can rewrite this as just a single term. The other thing we notice that's different is notice here we have our exponent, we have powers of x. We have an x squared term. That is okay. As far as we're concerned, the exponential function portion of this problem is not affected by that one bit. We try to get things in terms of a single exponential function of the same base on either side of the equation, drop the bases, and we're left with a simpler equation. So here we now have a quadratic equation, but that's okay. We know how to handle quadratic equations. Do not expect to see anything more difficult than a quadratic equation at this point. So I will refrain from putting in cubics, square root equations, all that fun stuff. I would hope you could handle those, but again, given time constraints, given pressure in a testing environment, don't expect to see that. Quadratics are going to be the nastiest thing we see. And then from here on out, this is old hat for us. We knew how to solve linear equations. We know how to solve quadratic equations, get everything on one side and factor it, and nothing is different from this point out. Now, we are going to run into some problems that look very similar to this later on down the road, where in fact we're not done once we get to this point. I'll go ahead and remind you, this will make more sense later on, but the reason we're done here is because we started with an exponential function. Remember that the domain of an exponential function is all real numbers. When we drew the graph of our exponential functions, there is nowhere where we had to say, oh, the function's undefined here, we can't draw it. So when we start with exponential functions, whatever we get for our answer here, that's the answer. We don't need to check things. Later on, we're going to be working with functions that have a more restricted domain. When we begin with those functions, we will need to double check our answer to ensure that these are in fact in the domain of the original functions. But here, there's no problem whatsoever. These guys don't cause any problems whatsoever.